to 2 to the minus log 1 over p of x times 2. What's 2 to the minus log 1 over p of x?
Sorry, it's a minus 1.
Minus? Oh yeah, it's minus 1. That's right. Sorry about that. So that makes that times 1/2.
1/2, yeah.
Yeah. Okay. 2 to the minus log 1 over p of x. So 2 to the, this is log 2, so 2 to the minus log p of x is 2 to the log p of x, which is what? P of x. So this is equal to p of x over 2. So that's really interesting because remember what I'm representing here. So I have f bar. In other words, the error is less than or equal to 1/2 p of x. What am I representing? So for instance, here is my f of x, and f bar is halfway between, or is on the halfway point of that interval. So this is f of x. This is f bar of x. Halfway up all of these intervals, that's where my f of x lives. So the maximum deviation I can get and still stay on that interval is 1/2 p of x. The length of that interval is p of x. So in other words, if I have an error not greater than p of x over 2, then my truncated version of f of x must be somewhere on here. So in other words, basically what I'm doing here is I'm constructing a representation of this interval, not necessarily of this particular point, f bar of x, but I'm constructing a binary representation of something that's guaranteed to be on this interval. These intervals are disjoint, so I can argue that f bar sub L of x is unique for all of these points.
If you then include that additional bit there,
yes,
then it will jump from the previous one to the other. You'll bring uncertainty.
Exactly. So that's adding the extra bit is why this works. So if I didn't, then I would have the full length here. So the idea is that f bar of x is at the halfway point of an interval of length p of x. What we also have is that f bar of x is less than f of x. Excuse me, sorry. That's true, that's not really the point. The point is floor f of x sub L of x is less than f bar of x. So my quantization, because all I'm doing is I'm dropping bits in the binary representation, it must be below f bar of x in this representation. It must be somewhere between f bar of x and f minus 1 of x. But f bar of x minus floor f bar of x sub L of x is less than or equal to, excuse me, is strictly less than p of x over 2. therefore, f bar of x and floor f bar of x, so L of x, are on the same interval. Furthermore, all of these intervals must be disjoint because, as I argued before, probability is increasing. So therefore, what I'm going to do is I'm going to say my code my code word for x, c of x, is equal to floor f bar of x sub L of x. So because the intervals are disjoint, c of x must be non-singular. So remember what non-singular means. Non-singular is a code where every code word corresponding to every input symbol is unique. So I can guarantee that because this code word lies on the same interval as f bar of x, and all the f bar of x lie on different intervals, and those intervals are disjoint, I can guarantee that all of these representations are unique. Okay, so that's a good start. But what I also need, we're really interested in prefix codes. Now remember, we showed I think 2 classes ago, that you don't lose anything by insisting on using a prefix code. So what we're going to do now is we're going to show that this code is a prefix code. So what we need is we need a non-singular code. We also need a uniquely decodable code, and we know that prefix codes are uniquely decodable. So let's show that. Furthermore, c of x is a prefix code. So how do I show that? What does it mean for a code to be a prefix code? That means it's, there's no code that has for whom a prefix is another code word. What does that mean in this case? What that means, so if the opposite were true, then it would have to be the case that some value of this for x1 is a prefix of f bar x2 sub lx2 for some x1 and x2. So what would that mean? These are binary representations of, these are quantized binary representations of